Okay, welcome to another video on. Okay, now in this video we'll have a look at the working of instrumentation amplifier and a specific design. So we will start with. So this is the circuit diagram. So we have resistors. So let us name this resistor as R1 RF. Let us also name this as same resistor R1 and RF. Let me name this as voltage Vx and let us name this as Vy. Let me find out what is V0. So to find V0, so using superposition theorem, I think now all of you by this time know how to apply superposition theorem and then get the values of output voltage. Now V0 can be written as V01 plus V02. So while finding V01, let us consider only Vx. So let us make Vy is equal to 0. While finding V02, let us consider only Vy. So let us make Vx is equal to 0. So from this V01, naturally when you consider only Vx, when you ground this acts like inverting amplifier, then it will be minus Rf by R1 times Vx. When you ground this, so these two are grounded, so it acts like an inverting amplifier with a gain of minus Rf by R1. Suppose if I take V02, when you are considering only Vy, when Vx is equal to 0, this acts like a non-inverting amplifier with the input voltage reaching here as equal to Vy times Rf by R1 plus Rf multiplied by the gain of this amplifier, which is nothing but 1 plus Rf by R1. So this will be the so from this we can write V02 is equal to Vy. So this will be Rf by R1 plus Rf. This I can write it as R1 plus Rf by R1. I can rewrite this, so this will go off. So ultimately I will write V02 as equal to Vy Rf by R1. Rf by R1. So we know the value of V01 and V02. So naturally what is V0? So V0 is equal to sum of these two. So that I can write minus Rf by R1. I can take it as common factor. Then this will become Vx minus Vy. So this will be the expression for the output voltage in terms of Rf and R1 and Vx and Vy, provided if these two are R1 R1, if these two are Rf and Rf. So this is the summing amplifier or a difference amplifier using operational amplifiers. So let us improvise this circuit for our instrumentation amplifier as this one now. So let me improvise this circuit by writing two more op amps and let this be plus minus, let this be minus plus. This is my V1, so let this be V2. I want to configure it as a voltage follower. So now I will write this as, there is a resistor here, there is one more resistor, there is another resistor. It is this is the circuit now. Let me connect this to this. Let me connect this here. Let me connect this over here. So let me name this as R2. This also as R2. Let me say this as RG. So this is actually Vx. Of course, same voltage Vx. This is Vy. Let us consider a current Ig flowing from Vx to Vy. So this is the circuit what you have. So this is now V1, V2. Now let us try to get the expression for V0 as a function of V1 and V2. So this is V0 as a function of V1, V2, and of course the resistors R1, R2, R3 and R1, there is no R3, R1, R2, RG and RF. So in terms of V1, V2 and all these resistors, we need to get the expression. The disadvantage in the previous difference amplifier was this source Vx and Vy were seeing different low resistances. So whereas these two sources V1, V2 will see a very high resistance, so that they will have a better impedance matching compared to applying the input at the difference amplifier. So that's the major advantage of this instrumentation amplifier. Instrumentation amplifier will have a very high input impedance for these two sources, or the sources which are used to amplify, which are supposed to be amplified, whose input has to be amplified. So these two will not be loaded by this instrumentation amplifier. Suppose if you consider same V1, V2 over here, they'll be heavily loaded because of these resistances R1 and RF. And of course they have different resistance of loading also, that we have discussed in the class. So now let us try to establish the expression or a relation between V0, V1, V2 and these four resistors, that is R1, RF, R2 and RG. So for that, let me write the expression. Of course we already know this expression. We already know the expression of V0 as a function of Vx and Vy. So what is V0 given by? V0 is given by this, which is minus Rf by R1. It is Vx minus Vy. This relation we already have it. Let me have a look at it. Okay, it's happening. We have already established the equation for this part of the circuit. Now the question is, I should relate Vx, Vy to V1, V2 and R2 and RG. So if I can replace this Vx and Vy by V1, V2 and these two resistors, then our job is done. So if you see this Vx and Vy, if you consider this as a current Ig, can I write the current Ig flowing between Vx and Vy as equal to Vx minus Vy divided by the overall resistance that is there from here to here? Is it not 2R2 plus Rg? So it's actually 2R2 plus Rg. You can see you have one R2 here, one more R2 here, which will become series combination 2R2, and there is a Rg. So this is the overall resistance between these two potentials. So potential difference is Vx, other one is Vy. Vx minus Vy divided by 2R2 plus Rg is your Ig. And I also know that of course there cannot be any current flowing here, so this current is 0, this current is also 0. So whatever current that is flowing here, the same current flows here also, So I know that because of this virtual ground, there is no potential difference across this. Here it is 0, the potential difference across this is 0. So if the potential difference across this is 0, whatever is the voltage, same is the voltage here. So it is V2 and it is V1. So this is V1. So I can again write one more expression for Ig as V1 minus V2 by Rg. V1 minus V2 by Rg. So I can able to express the Ig which was from Vx minus Vy by the overall resistance, that is 2R2 plus Rg, is one expression. There is one more expression which is available for Ig, which is current flowing through this resistor Rg. It is nothing but V1 minus V2 by Rg. So this is the second expression. So let us equate them. So I can write Vx minus Vy by 2R2 plus Rg is equal to V1 minus V2 by Rg. So from this I can write Vx minus Vy is equal to V1 minus V2 into 2R2 plus Rg by Rg. So this ultimately I can simplify it as Vx minus Vy is equal to V1 minus V2. It is 1 plus 2R2 by Rg. So we got the relationship between Vx and Vy in terms of V1, V2, R2 and Rg. So once you have a relationship between Vx, Vy and V1, V2 and R2, Rg, you can plug this Vx, Vy by this. So what is V0 now? V0 is equal to minus Rf by R1. What is this Vx minus Vy? It's this. It's actually 1 plus 2R2 by Rg into V1 minus V2. So this is the expression. So I have got the expression for V0, that is this output voltage in terms of V1, V2 and all 4 resistors. You can see this is the expression of output voltage in terms of V1, V2 and all 4 different resistors. You can see there is a negative sign and this is V1 minus V2. So this is also possible to write V0 as equal to Rf by R1 1 plus 2R2 by Rg into V2 minus V1. This negative sign I am taking it off and I am just making it flipped off. So this is also true. This is also. So this is a very simple proof of what is the expression for V0 in terms of V1, V2. This we know very easily. And next is you have to consider this circuit and then show what is Ig in terms of Vx, Vy, which is this, and you also indicate or equate this Ig in terms of V1, V2, it is this. Equating this, I'll get the relation between Vx, Vy and V1, V2 and R2 and Rg. Plug it in this equation, you get the final expression of the output voltage of the instrumentation amplifier in terms of the input and all 4 resistors. Assume that you are supposed to design V0 is equal to some 10 times V1 minus V2. So this is what is required. So 10 times V1 minus V2. But in this expression what you have, if the input has to, suppose if it is V1 minus V2, you should have a negative sign. Suppose if this is the requirement, so what you can do is you can replace this by V2, you can replace this by V1. So now if you replace this by V2, V1, so can I able to write this as the expression now? Now if the design is expected to be 10 times V1 minus V2, so what is my circuit? My solution would be like this. So this is my solution. I am writing the solution here. So I will write this. Now be careful, the input is applied to non-inverting terminal, the input is applied to non-inverting terminal. This is the inverting, this is the inverting, this is R2, this is Rg, this is R2, and you have a resistor R1 and you have a resistor same R1. Okay, let me just, this is resistor Rf. I have one more, this is minus, this is plus, this plus will go here, this is grounded and this will go down here, and this is now Rf, this is R1, this is R1, this is Rf. And for this circuit, because you want to have 10 V1 minus V2, this has to be V2, this has to be V1. So now what I have to make? I have to make this Rf by R1. Now expression for this would be Rf by R1 1 plus 2R2 by Rg into V1 minus V2. This is the expression what I will get with this as V2 V1. So now this we know as it is, but this has to be a value of 10. So this should be of value 10. So how do I get this value of 10? One of the possibilities, you make this ratio 1. So let Rf be 10k this will also be 10k. Then make sure that this is 1 plus 9. If this is 9, then you get 10. Of course, this will go off, you will get a gain of 10. So now what is the condition? 2R2 should be, okay, 2R2 by RG should be 9. So what you are looking at now? So 2R2 is equal to 9 RG, or R2 is equal to 9 by 2 RG. So now let RGB be around 10 kilo ohm. If RG is 10 kilo ohm, then what is R2? R2 is equal to 90 by 2, which is 45 kilo ohm. This is kilo ohm. So now what is the design values? For this particular case, R1, R2, R1, RF, R2 and RG. R1 is equal to 10k, this is equal to 10k, then R2 is equal to 45k, whereas RG is equal to 10k. If you use all these values and substitute here, so do you have it as 10k by 10k for this RF by R1, then it is 1 plus, what is 2R2? 2R2 is 90k, what is RG? 10k into V1 minus V2. So can you see now this will go, this is becoming 1 and this is 9. Is it not 1 plus 9, 10? Is it not 10 V1 minus V2? You have 10 V1 minus V2. So this way you can very comfortably do the design. Assume that you have a design where you are expected to design something like minus 50 times V1 minus V2. Now the gain required is output voltage should be minus 50 times so and so. Can you see, is it not in the same lines as that of this expression? Is it not in the same lines as of this expression? In such case, I will retain this as V1, I will retain this as V2. So what is my circuit? My circuit looks like this. This is a circuit. This is now again plus. I'll apply the input voltage V1. This is inverting terminal. Let me connect 3 resistors. R2. Of course, you have to be very careful with the naming of the resistors. This has to be R2, this has to be R2, this is RG. Then this is going to inverting terminal. From inverting terminal it goes there. This is a non-inverting terminal which is V2. And now you have R1 and you have a resistor RF. This is my third amplifier. So this is going to inverting terminal, this is going to non-inverting terminal. From here this goes to R1, this is now RF, this is R1, this is RF, this is V0. So V0 is equal to now minus RF by R1 into 1 plus 2R2 by RG into V1 minus V2. Now as per this you can see this should be 50, this should be 50. If this is 50, then the rest of the equation follows the same. So now what you can do is, of course there are a number of possibilities. Either you can make this, make sure that this ratio is always more than 1. So I can make this as 10k. So now this should be 1 plus and this ratio should be 49. This ratio should be 49. So it is so now what is this? 1 plus 2R2 by RG should be 50. So that 2R2 by RG should be 49. Therefore R2 is equal to 49 RG by 2. So if RG is if RG is 10 kilo ohm, then what will be your R2? Your R2 would be 490 by, it will be 49 by 2. 49 by 2 will be 245 kilo ohm. 245 kilo ohm. So here it is. This will become 245 into 2 would be, okay, it is 2 times 245k by 10k into V1 minus V2. If you substitute that, is it not 245 into 2 divided by 10? Can you see it is 49? 49 plus 1 is 50. Is it not minus 50 times V1 minus V2? Are you not getting the same design? So this way you can able to comfortably do the design. Okay, thank you.